Nampak tak? Nampak tak? Hello? Dengar tak suara saya?
Dengar.
Dengar.
Okay. Okay, so saya nak mulakan. Okay, boleh nampak tak slide PowerPoint ni?
Boleh.
Okay. Laptop saya ni macam ada hang sikit, so saya harap you all boleh boleh nampak dengan jelas lah Okay. So for today we're going to continue with our chapter 1. Okay. For this slide, learn about the electromagnetic spectrum. Okay. So why I want to explain about the electromagnetic spectrum, because the electromagnetic itself is a source of energy, okay, for the instruments. Okay. If there is no electromagnetic, there will be no instrument. So what I want to say here is that electromagnetic energy is the main compartment in any instruments, especially in spectrometer. Okay. Okay. Boleh nampak tak ke perlu saya tunjuk satu slide ni?
Boleh Dr.
Hello?
Hello, Dato'. Dengar, dengar.
Dengar eh? Macam mana, macam mana? Hello?
Dengar Doktor.
Dengar. Okay.
Dengar, Dato'. Dengar, dengar.
Okay, so okay, boleh nampak tak slide saya?
Boleh, Dato'. Boleh.
Okay. Okay. So okay, I just want to repeat balik. Okay. What is the purpose you learn about electromagnetic spectrum? Okay, is because uh, for instrument, especially like UV spectrophotometer, they will need these kinds of energy, okay, in order to bombard the atoms in the molecule, okay, to give the signal. So if there is no source of energy, then the instrument will not work out, okay. So this is the main thing that you need to understand, okay. Okay, so first of all, what is electromagnetic spectrum? Okay, as you all know, electromagnetic spectrum is a series of lights. Okay, like UV, ultraviolet, visible light, infrared light. Okay, X-ray, gamma ray. Okay, and all of this is kind of lights. Okay, and basically these kinds of electromagnetic is uh, is a continuum. Okay, it's not like single what we call it, discrete. I mean discrete. It's not discrete, but it's in a continuum version. Okay, and from this electromagnetic wave that bombard the molecule in your sample, they will trigger to a vibration. Okay, because just like one atoms, okay, when it receive one electron from outside, from the external, it will have a new or increase of energy. Okay, so this is the basic concept of the instrument. Okay. Okay. So what is the electromagnetic spectrum? Okay. So what is the electromagnetic spectrum? It can be radio waves, okay, from the cell phone, from the microwaves, okay, even radar, okay. So all of this is kind of electromagnetic, okay, electromagnetic spectrum. Okay, so let's look for this one. Okay, I believe that most of you already macam pernah lah tengok this kind of uh, susun apa, susun jalur orang panggil dia bermula dengan a very low frequency until a very high frequency. Okay, so this is what we call as the electromagnetic spectrum. So what we can say from this spectrum is that when like radio will have a very low frequency. Okay, so when it have a very low frequency, we can estimate that it will produce a very low energy. Okay, so how can I say like that? Because it depends on the formula. Okay, I get this information from the formula. Okay, let's look for the next one. So this is the formula. Okay, no. This is for the speed. Okay, but what I want to tell you is that the energy. Okay, energy is inversely proportional to the wavelength. Okay? So this is the things that you need to know very well. Okay, from the formula of E equals to HC over lambda. Pernah dengar tak formula ni? Class? Have you heard about E equals to HC over lambda?
Pernah.
Pernah kan?
Pernah.
Okay. Okay. Thank you for your response. Okay. 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 So now let's look for the speed. Even though we have many kinds of wave like radio wave, ultraviolet waves, okay, gamma, even gamma waves, okay, gamma ray, all of that travels at speed of 3 times 10 to the power 8 to the power of 8 meter per second, okay, in a vacuum. So this is the fixed uh, velocity of light, okay. So which we can get from the formula of speed equals to frequency times wavelength. Okay. Okay, next. So what is the relationship between wavelength and frequency? So by the time we want to understand the relationship, we must know the formula. Okay, so just like what I mentioned to you just now about the formula of energy equals to hc over lambda. Okay, so in this case okay. Okay, tak apa. Okay, from this formula, you can estimate that when you have a very high speed, okay, so the frequency will decrease or increase. Any answer? When you have a very high speed, what about the frequency?
Increase.
Increase. Okay. So what about if you increase the frequency? What happened to wavelength?
Decrease.
Decrease. Okay. I
Decrease.
hope. Okay. I hope that you can understand from the formula how we can estimate either it is a direct proportional or inverse proportional. Okay. Okay. I hope that there will be no problem to read the relationship from the formula. Okay. Okay. So as wavelength decrease, frequency will increase, okay, because you know that frequency is inversely proportional towards wavelength. Okay. Okay, so this is the most important that by the time we want to relate the energy with the wavelength. Okay, because as you know, okay, I believe that most of you already done or do the hands-on for UV spectrophotometer during your first year. Okay, and what you can get is the output is what we call a spectrum. Okay, and the y-axis is the absorbance, and the x-axis is the wavelength. Okay, so by the time we want to understand why we choose wavelength as the x-axis, okay, so this is because we want to relate the wavelength with the energy, okay, because we cannot calculate the energy directly, okay, so that's why we need to choose a certain wavelength, okay, so that we can know how much the energy does your molecule absorb. Okay, that is the idea. Okay, so in such a way for you to understand in the instrumentation compartment, so you must know that short wavelength will have high frequency, okay, or a long wavelength will have a low frequency. So this is the things that you already understand from the previous slide. Okay. Now, what we can say when it comes to relate to the energy. Okay. So here you can see when you have high frequency of waves, it will have high energy. Okay, it will it will absorb the energy at a very high amount. Okay, okay, ada apa-apa soalan tak? Do you have any question about this part? It's clear?
Ya, Doktor.
Okay, now so here I hope that you can do by your own. Okay, just fill in the table and to see the relationship between these three parameters. Okay. Okay, so here I want to explain about the real electromagnetic. Okay, when we talk about electromagnetic, we always refer from radio to gamma ray. Okay, so you must know this order. Okay, so that you can understand why each of these electromagnetic is in this order. Okay, there's a reason behind that. Okay, so what you can see here is that radio have a wavelength of 10 to the power of 3 meters. Okay, so it shows that radio have a very long wavelength. Okay, so when it has a very long wavelength, it will produce a very low of energy. Okay, that's why in instrument, basically we don't use radio as the source of energy because the energy is considered low. Okay, that's why kita boleh, you can always hear the radio. Okay, because the energy that when you use radio is not very high, it will not affect your body. Okay, so it will not harm your body. Okay, okay, so for the next one is a bit higher, okay, of energy but low wavelength, okay, shorter wavelength, is a microwave. Okay, so this microwave is just like what you use at home. Okay, next is infrared. This is IR, so a bit high of energy compared to radio and microwave. Okay, and then next is the visible. Okay, the visible light is actually the energy is lower compared to ultraviolet. Okay. Okay, so next is X-ray, and the next one is gamma ray. As you can see that the wavelength for gamma ray is very short. Okay, very short. So when we talk about wavelength, we always consider the what we call as the sinusoidal. Pernah dengar tak? I don't know how to pronounce it very well, but the gelombang wave, okay. So this is the things that very important because when we try to relate the wavelength, we need to know that either it is a short wavelength or high or longer wavelength. Okay. Okay, so this is the more colorful colorful slide, okay, so that you can see that the relationship is there, okay. By the time you want to increase the energy, okay, the wavelength will be decreased, okay. So here you can see also the size, okay. The size is about like for radio is bigger, okay. And when we talk about gamma ray, they are focusing on the nuclei, okay, the nucleus of the atom, okay. Okay, next, so for the radio waves, is a very low energy of waves, okay, and longest wavelength. So this is the radio waves that we use through our cell phone, okay, and also the radio, okay. If you have any question, you can ask me, okay. Okay, so next is microwaves. Okay, microwave is like for the communication, for the medicine and consumer use, like oven. Okay, so they simply use this kind of waves. Okay, the microwaves. Next is the infrared waves. Okay, basically this is the kinds of wave that we use to detect the heat. Like right now we have one sensor that can display the heat of the body. Okay, like if you are having a fever, they can detect from far. Okay, so it can estimate the range of the temperature. Okay. Okay, so now we're talking about the visible light. Okay, so visible light is the common the common lights. Okay, the common wave that we always use. Okay, that producing various of color. Okay, so what is the color? It is red, orange, yellow, green, blue, indigo, and violet. Okay, so I hope that you can memorize this order. Okay, so that you can understand why each of these color in this order. Okay, so from this order, you can see that red has the lowest frequency. Okay, so when a red has lowest frequency, what we can say about the energy? Any answer? No? Okay. So the order of this color play an important point. Uh, I believe that most of you will ask, why not orange first? Why not yellow first? Okay, the reason is because of this. Okay, because um red, okay, red is closer to the infrared, so the color will be like quite similar to the infrared. Okay, so it will have the very lowest frequency. Okay. Okay, so here you can see for the ultraviolet and visible light. Okay, the range for visible light for wavelength is about 400 nanometers until 700 nanometers. Okay, so as you can see that red have close to 700 nanometer. Okay, so this is quite high number of wavelength. Okay, okay. So when it comes to the violet, the color for about 400 nanometers, you can see that the energy is become higher. Okay. Kalau if you have any question, you can just interrupt. Okay. Don't wait until the end of the class. Okay. Okay. So now let's look for the ultraviolet waves. Okay. Okay, before we continue with the ultraviolet waves, okay, I just want to mention to you here the visible light. Okay, so basically when you try to when you use spectrophotometer, okay, you will see that your solution is in a colorful color. Okay, I mean the solution is blue, sometimes red. Okay, so this color is actually uh, if your sample is a colorful, okay, you can simply use the range of wavelength between 400 nanometer until 700 nanometers. Okay, so that is the important thing, so that you can choose a very good range for your sample. Okay, so next is the ultraviolet waves. Okay, so in these ultraviolet waves, it is a bit higher energy from compared to visible light. Okay, and so you can see that ultraviolet can cause skin cancer, blindness in humans. Okay, so as you can see that ultraviolet can give you harms. Okay, so that's why ultraviolet need to be handled with care. Okay. Okay, next is the X-ray. So X-ray is the I can consider as a high energy waves. Okay, it has been used in medicine, like for X-ray to detect any crack on the bones, or industry. Okay, and astronomy. Okay. Also, this can cause cancer. That's why you cannot do X-ray like for medical checkup more than twice. Okay, in a year. Okay, it will give harmful. It will become give you adverse effect. Okay. Okay, the last one is what we call as a gamma ray. This is a very high energy of in the electromagnetic spectrum. So what we can say that this kind of gamma ray is, for instance, like the energy from the sun. Okay, this is the kinds of energy that give very high impact, okay, towards sample. Okay, so again, this electromagnetic spectrum you can see very clear. Okay, so when we talk about wavelength, it's always about the waves. Okay, when we talk about wave, there will be always an amplitude. Okay, and what we call as a mm, um, amplitude lah. Okay. Okay. So next, okay, now there are a few questions here. So what is the relationship between frequency and wavelength? Any answer?
Inversely proportional.
Inversely?
Proportional.
Okay. Next, what characteristic of gamma waves give them their high energy? What characteristics?
It has low wavelength.
Okay, shorter wavelength, right? Okay, good. Okay, what does Roy G. Biv mean? What part of the electromagnetic spectrum does it refer to? ROYGBIV. These are terms in the ultraviolet or visible light?
Visible light.
Visible light. Okay, good. Okay, so I hope that you can know red, orange, yellow, green, blue, indigo, violet. Okay? Okay, next, which color is more energetic, red or yellow? Which one have a more energy? Any answer? Red have a longer wavelength. Am I right? Okay. When red have a more longer wavelength, so it will have a short. It will have a small amount of energy. Am I right?
Yes.
Okay, good. So compare red. When you want to compare red color and yellow color, so red is more or less.
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 Less. Okay, good. Okay, so that is the thing that you need to understand first before we proceed with the instrument. Okay, this part is very important. Okay. Okay, which type of wave travels faster, gamma or radio? So
Gamma.
this one you need to refer to speed, right? Okay. So what is the answer?
Gamma.
Okay. Can you prove how you can say that gamma travel faster compared to radio? When we talk about faster, we are referring to the speed. Am I right?
Yes.
Okay. When we talk about speed in the electromagnetic spectrum, speed always travel at 3 times 10 to the power of 8 meter per second. That is the fixed value of speed. Okay, so you can consider that gamma and radio have the same speed of light. Okay. Okay, why are microwave more dangerous than radio wave? Why microwaves more dangerous than radio waves? When we talk about dangerous, more dangerous, it means that we refer to the high energy. When the electromagnetic produce high energy, so it will give harmful to you. Okay, so this is the terms or the definition from the more dangerous. Okay, so when we talk about this, we always try to understand the energy, the amount of energy produced. Okay, so like microwave more dangerous than radio wave, is it true, and why? Okay, it's true because the energy of microwave is higher compared to radio waves. Okay. Okay, next. You have just been involved in traffic incident that leaves you stranded on the side of the road. Which part of the electromagnetic spectrum will be of the most use to you and why? Okay, so try to answer this, try to think about this. Okay, so this is the following answer. So you can, this is the answer for the questions. Okay, so now I want to proceed with noise and error. Can I? Just a few minutes more. Okay, boleh ke?
Boleh doktor.
Okay,
Boleh doktor.
okay. Okay, so now we're going to for the signal and noise. Okay, so I believe that most of you already understand the relationship between the wavelength and the energy. Okay, so in this first slide, you can see that it's a sinusoidal of wave. Okay, so in the source of energy, okay, we always address the energy with the wavelength. Okay, so that's why when we talk about wave, there will always an sinusoidal shape, okay, of the signal. Okay, so we ideally we can consider that the signal will be like smooth, like this one in the first slide. Okay, this is smooth data. Okay, however, what happened when we use different kinds of source of energy, we can get like this. Okay, this is the problem that we need to solve, especially in the instrumentation method. Okay, so basically we want to solve the presence of the noise. Okay, okay, when we talk about the signal and noise, what is the difference between these two? Okay, signal is the sample response. It means that your analyte give response. Okay, so that is what um, mean by signal. Okay, the signal of your analytes. Okay, we want to increase the signal of your analytes. Okay, and here we also have a blank response. Okay, basically we will consider, okay, the blank response will give you a straight line like this one. Okay, however, that is not what happened. They give you like this. Okay, and how you can overcome this problem, okay, is actually by using the software or hardware. Okay, we will go further for this part. Okay, okay, so by the time your sample response or your sample signal increase, okay, you can exactly determine that your analyte is present with a certain amount of the uh, response. Okay, so don't get confused between signal and response. Okay, so signal is the something that you give that you can determine from the output, but for the response is the y-axis. Okay, the y-axis of the output. Okay. Okay, so basically you will face this kind of problem which is called drift. Okay, so drift is the baseline changes slowly with time. So basically drift is the things that always occur for liquid chromatography and gas chromatography, because uh, the x-axis is the time. Okay. Okay, now let's look for the noise. So here is the random time dependent change in the instrument's output signal. Okay, so sometimes the random error is a bit difficult to overcome. Okay, and basically noise is something that very difficult to overcome. Okay, but you can reduce the effect of noise. Okay, and you can increase the signal. Okay. Okay, when you have a very high noise, okay, so the accuracy will become lower. Okay, the result or the signal you want will not become accurate. Okay, that is the problem. Okay, so we have different kinds of source, so we will look after this. So that's why it is important for you to detect the limit. Okay, the detection limit. Detection limit here is same like limit of detection. Okay, LOD. Okay. Now let's look for the signal to noise ratio. Okay, why we want to have this kind of ratio? Because we want to overcome the noise problem. Okay, and at the same time we want to increase the signal. Okay, so this kind of ratio is to compare between signal level and noise level. Okay, so here you can see noise is independent of signal intensity, and basically signal to noise for LOD is 3. Okay, the ratio is at 3. Okay. Okay, now let's look for the source of noise. Okay, it can be from chemical noise. Okay, so chemical noise is something that you cannot control the variables, okay, because it comes directly from your sample or from the certain parameter, okay, like temperature, okay, pressure, humidity, and vibrations. Okay, and the other one is instrumental noise. Okay, this kind of instrumental noise can be overcome. Okay, there are like thermal or Johnson noise. Okay, so basically for the thermal and Johnson noise, okay, this kind of electronic noise generated by thermal agitation of the charge carrier. In this case, the charge carrier is the electron. Okay, so by the time the instrument run at high temperature, it will affect and give the thermal noise. Okay, so how we can overcome this thermal noise? Only by making the temperature lower. Okay, but not very low, because if the temperature is very low, then the analysis will not be conducted in a proper way. Okay, so you will not get the output. Okay, so there will be an what we call as an optimum temperature. Okay, so this is the things that you need to know. Next is short noise. Okay, short noise or poison noise is due to discrete flow of carrier in the device. Okay, so in this short noise, for me, it's very tricky and not easy to be overcome. Okay. Okay, so next is the flicker noise. Okay, the flicker noise is electronic noise that dominates at low frequency or low frequency offset from oscillator. Okay, so from these kinds of noise, basically it happens at the baseline. Okay, always occur at its baseline. Okay, so how we can overcome this problem is using high pass circuit. Okay, all of this is actually you learn a lot in the electrical engineering. Okay, sorry for the sound. Okay. Okay, so let's look one by one the thermal noise. Okay, so here you can see that this kind of noise caused by the thermal agitation of electrons or charge carrier in resistor, capacitor, and other elements. Okay, so the charge inhomogeneity. So from this charge inhomogeneity, okay, it will produce the voltage fluctuation. Okay, so how we can overcome this problem is depends on this formula. Okay, so here you can see this formula. The root means square for noise voltage. Okay, so what is this formula? So this formula, okay, so V, the voltage, okay, equals to square root of 4 times K. K is the Boltzmann constant, okay. T is the absolute temperature, okay, and B is the noise bandwidth, okay, and R is the resistance, okay. So basically, when you try to load to lower the temperature, you will lower the thermal noise. Okay, so basically that is the 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 method that we can use to overcome thermal noise. Okay. Okay, now let's look for the short noise. Okay, so short noise, we can use, I mean, electronic noise that dominates at low frequency or low frequency offsets from the oscillators. Okay. Okay, so this is the flicker noise. Okay, so basically flicker noise will have a inversely proportional to the frequency signal. Okay, 1 over f. Okay, and it always occur at the baseline. Okay, during offset. Okay. Okay, now for the environmental noise, okay, that what is this kind of noise? This kind of noise is actually comes from surrounding, okay, um, more towards the electrical compartment, okay. Okay, so for instance, like at the compartment of to convert to the electrical signal, okay. So that is one of the environmental noise. Okay, so signal to noise enhancement, we have two types of signal to noise enhancement. We can use hardware. Okay, so this is the list of the hardware that can be used to improve the signal to noise. Okay, like grounding, filter, chopping, lock-in amplifier, and modulation. The next one is by using software. Okay, so basically software we use in many kinds of instrument. Okay, especially when the signal is converted uh, to the output. Okay, okay. So there are a few. Okay, ensemble averaging, boxcar averaging, digital filtering, and also correlations method. Okay. So for the ensemble averaging, so we can use for this ensemble averaging. The successive set of data stored in memory as array, and then the point by point is sum up, okay, and then they make it average. Okay, for this example, okay, by the time you have more than 3 times of scan, okay, when you scan a lot, okay, it does give you an average. Okay, so when you have this average, okay, it will actually increase your signal and lower the noise. Okay, so this is more towards the electrical engineering. So we can do that. Okay, so that like for this one, the first scan, you can see there's a lot of noise. Okay, this one. Okay, by the time you run until 50 scan, when you do the assemble averaging, you see the signal become higher and the noise will remain lah. Okay, because noise will always remain. Okay, so by the time you do the 200 scan, the output will become better. Okay, so you can see that enhancement occurred. Okay, when you do the assemble averaging. Okay. Next is the boxcar averaging. Okay, so for the boxcar averaging is to smooth the irregularities. Okay, they try to smooth the peak. Okay, but this method is a bit it has a drawback because it will some data will not be there. Okay, for example, like this one, you can see that you have a set of data, and then when you do the boxcar averaging, so you can see that there are a few of data is missing. Okay, so this is the drawback of the boxcar averaging. Okay. Okay, so for the digital filtering, so basically we use the Fourier transformation. We also implement the assemble averaging. In my opinion, assemble averaging is the best one. Okay, and we also have the least square polynomial smoothing. Okay, least square polynomial smoothing ni macam yang in your Excel. Okay, you can see that when you have uh, when you try to produce the calibration curve, okay, you can see that um, uh, when you want to produce the calibration curve, you can see by depending on the R squared value, okay, the linear regression line, okay, value. Okay, next is correlation. Okay, so this is one example for the Fourier transformation. Okay, as you can see that before you treat with a Fourier transform, the data is like this. Okay, too much noise. Okay, and after that, by the time you do the Fourier transform, the noise become lower. Okay, so this is the one thing or the one benefit that you can get. Okay, in order to improve the signal to noise ratio. Okay. Okay, so that's all for today, and I hope that you can at least get something from today's class. And please don't forget, to fill in your attendance because that is important for our record. And do you have any questions?
No, Doctor.
No? Okay. Okay, I hope that you can, kalau tak dapat semua pun dapat sikit lah Okay. And I will give you the recording after this. And I hope you can understand very well, okay, for today's class, okay? Okay. Okay. So tak ada apa-apa Dah tak ada apa-apa soalan? Do you have any question?
No, Doktor.
Okay.
No, Doktor.
Ni you all masing-masing dekat rumah ke apa?
Kat rumah.
Ya, yeah. Ada yang dekat UMP ke? Tak ada.
Tak ada kot.
Tak ada. Semua kat rumah ya. Okay. Okay, I hope that you can survive duduk di rumah dan sambil tu belajar. Okay. But for me, kalau saya jadi student, okay, for me is a bit difficult lah. Okay. a bit difficult because environment lain. Okay, and I hope that you can survive this semester and the following semester. Okay, so I think that's all for today. And if you have any question, you can ask me directly through WhatsApp. Okay. Okay. Thank you, class.
Thank you, Doctor.
Thank you,
See you
Doctor.
next week. Okay. Bye bye.
Bye.
Thank you.
Bye.